So let us start with the second part of our lecture on stack. And in this lecture, we are going to see the implementation of stack using linked list. Now, in case of the linked list, so in case of the insertion in a stack using a linked list, it will be a single linked list operation. In case the input, in case of the insertion, so we call this the push operation. And here the input will be the stack and the value which we want to insert, and the output will be the stack with the added element. The first 4 steps will be same like any linked list operation, that is first checking for the available memory space. So the available memory space at the first has been given to my new node, and then it will be pointing to my next node. So the first available memory space has been given to my new node, then it will be pointing to the next available node, memory space in the OS. The new node arrow data part will be equals to the value which I have shown, and then we have to check. Now we have to start. So like linked list, we have a start pointer. Now here the start pointer, what was in case of a linked list? Let us compare. So in case of a linked list, the starting pointer always points to the node which has been inserted at the first. So let me write down here. So in case of single linked list, start pointer always points to the first node which was created. So whenever the first node is created, start node, whatever we put, start node always points to the first node which was created if we are inserting it at the end of the list. Remember, if we are inserting an element at the end of a linked list, start node will always be pointing at the first node which was created in case of insertion at end. But if the insertion was at the beginning, then start pointer always points to the last node which was created. In case of insertion at the beginning, this is a very important point. We will see that this is very important in case of a top, in case of a stack, because the top elements always points to the last node which was created. So looking at this, we can say that in case of a stack implementation using single linked list, insertion always takes place at the beginning of the list. So this is what was my point. Now initially when top is null, so what we do? This is my only node, so I can safely make the next pointer part of this to be null. And then what I can do is that, so I can make top point to my new node. So this address becomes 200. Now suppose this is not my case and I have created a new node. And this new node, so this is my Avel. So now new node is here. New node 2, let me write it down, new node 2. This is my new node 1 and this is my new node 2. So Avel will no longer point here. It will move to the next available memory space. Let let it be here. And so what I have to do, again I have to make the value, let it be 40. Now if top is not null, what I have to do, I have to put the value of this existing node to the next pointer part of new node. So I make 200 here. So once I do this, what happens? This linking is over. So this node points to this node. Now what will happen? This is my newly inserted node, maybe with a value 500. That is memory address 500. So I have to simply make top point to this node. So I have to make top point to this. So my linking is over. So we see that the newly inserted node becomes the top element. So this is similar to insertion at the beginning of the list. If we think about the complexity will be naturally order of 1, because here we have seen that in case of insertion at the beginning of the list, it's only a standalone operation, constant time operations, so it is order of 1. Now let us look at the deletion algorithm in case of a stack using linked list. Now if I see the deletion using linked list, then it is similar to deletion from the beginning of the list. Now input will be the stack and the output will be the stack, same thing. Now this is the representation of the stack. So first we have inserted 30 and then we have inserted 10. So it is at the top of my stack. Now if I want to delete, first I have to check whether top is null or not. So checking for a empty stack. So underflow. If not, what I do, I set a pointer to my element which is to the node which is pointed to by top, because that is my top element. So this is PTR. And then what I have to do, I have to put the address of this next part of PTR to top. So I can either write top equals to top arrow next, or I can also write PTR arrow next, because both are pointing to the same address. So we can either write it to be PTR arrow next, or we can write it to be top arrow next. Anyone is correct. So once I do this, what is going to happen? So this link will be over. So what is there in PTR arrow next or top arrow next? 200. So instead of 500, now it is 200. And what is meant by 200? So it is pointing to this node. And we delete, we free PTR. So this is deletion. This is similar to deletion from a linked list at the beginning of the list. And we already know that complexity to be order of 1. Now, let us see the peak operation. Now, before going to the peak operation, say when we are going to display, suppose we want to display this list. How we are going to display? So the display will happen from the top part. So it will be displaying me like 10, 30, and so on. So whenever, if we see the display like this, then we should remember that 10, that is which is at the top of the element, was the last element which was inserted. And the first element, that is the last element which will be shown, is the first element which is inserted. So you can try it out as an assignment, that if we want to see the order in which the insertion happened, that is if we want to see this order, that first 30 has been inserted, then 10 has been inserted, how we can do that with the help of a linked list. Usually the display, because it starts from the initial starting pointer, which is top in this case, it will be showing you 10, 30 and so on. But your assignment is, if we want to display in the reverse order, that is we want to check the order in which it was inserted, that is 30, 10 and so on. How you can do that, or how you can implement that. I'm talking about the implementation issue. How can you can implement that? So that you can try it out as an assignment. Now the pick operation is very simple. We have to first check whether top is equals to null or not. So if it is not null, what we do, we put the top arrow data to val. Why? Because if we look at the simple representation, so this is my top. It is pointing to the top element. So I want to see the top element. So if this is supposed to be 10. So I simply put in val the top arrow data. So what is there in top arrow data? 10. So it is going to display and return the value. So this is the pick operation. Again, it is order of 1 because it's a constant time operation. So this ends the implementation or the algorithm for implementation of a stack using a linked list. You can try out the different, like if you want to access, as I told, you have to access the top element of a, generally that is the operation which is done to access the top element of a stack. Or you can also do search for a particular value, whether it exists in a stack or not, but that will be similar to what we usually do for a array implementation or stack linked list implementation. So in the next lecture, we are going to check about the applications of stack in most of the important evaluations. And then we can go for other type of stack applications like in recursion and everything. So if you have any doubt, you can comment in the comment section and then we can try out those algorithms also. Thank you.